Hello, everyone. I'm Dr. An. In this module, I will offer you a comprehensive introduction to artificial intelligence. I will cover the following basic but crucial topics, including what is AI, what is the relationship between AI, machine learning, and deep learning, what is the key difference between machine learning and symbolic AI, why use machine learning, what are some of the real-world applications of AI, what is supervised learning, what is unsupervised learning, what is semi-supervised learning, what is reinforcement learning, the issue of insufficient quantity of training data, the issue of non-representative training data, the issue of poor quality data, the issue of irrelevant features, what are overfitting and potential remedies, what are underfitting and potential remedies, what is the difference between model training, validating, and testing, what are the common Python modules for machine learning and data analytics, what are Jupyter Notebook and Google Colab. Many contents of this presentation were adapted from the textbook Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow, second edition by Aurélien Geron in 2019. I have no conflict of interest with the textbook author, and I highly recommend this textbook to machine learning beginners. Now, let's dive into today's module. Hello, everyone. I'm Dr. An. Let's dive into the introduction to artificial intelligence and machine learning. So first of all, what is artificial intelligence? In the 1950s to the late 1980s, we had a symbolic AI, which believed that human-level artificial intelligence could be achieved by having programmers handcraft a sufficiently large set of explicit rules for manipulating knowledge. While symbolic AI proved suitable to solve some well-defined logical problems, for example, playing chess and checker, it quickly turned out to be intractable to figure out explicit rules for solving more complex, fuzzy problems such as image classification, speech recognition, and language translation. And now we moved into the modern AI era, meaning machine learning. So the modern AI or machine learning symbolizes the effort to automate intellectual tasks normally performed by human beings. There are different terms, for example, artificial intelligence, machine learning, and deep learning floating around, so let me clarify them one by one. First, artificial intelligence is the all-encompassing term, including both the symbolic AI, which is the rule-based approach, as well as the modern AI, meaning machine learning. Therefore, machine learning is a subconcept within the artificial intelligence. And a specific machine learning method using neural network is called deep learning. So therefore, deep learning is a subconcept of machine learning. What is the difference between the symbolic AI, meaning the rule-based approach, and the modern AI, meaning machine learning? Well, in the symbolic AI, we provide the handwritten rules as well as the data to the classical programming, and the output are answers. Whereas in machine learning or modern AI, we provide data as well as answers to some machine learning algorithms and output the rules. Well, which one is easier? Definitely the machine learning approach. For example, we can provide the images as well as labels to the images, such as which image is a dog, which image is a cat, to a machine learning algorithms, And then we come up with the rules to differentiate between a cat image and a dog image. Whereas in the symbolic AI, we have to carefully write complicated rules to differentiate a cat from a dog, which is often too complex or difficult to write. Why use machine learning? Well, here is another example. Consider that we want to write a spam filter using the traditional programming techniques. We have to come up with some explicit rules to differentiate regular emails from spam or junk emails. Well, maybe we think in the rules, we should write any emails that contains 3 asterisks or 3 question marks or some keywords, for example, lottery or win, should be classified as spam email. But this may not be entirely true. And there might be some exceptions, some emails that have such words but may not necessarily be a spam email. So therefore, you have to spend a lot of time and efforts try to write those rules. Some of the rules may not work well with each other and have some conflicts. And after you've written the rules, you feed the email into the rules, and then you evaluate the output in terms of, for example, the accuracy of classifying emails into spam or regular emails. Whereas in the machine learning approach, we can design a spam filter by feeding your emails as well as their corresponding labels, meaning whether this email is a spam email or a regular email, into a machine learning algorithms. And then you train the algorithm so that the algorithm is going to learn from the data and gradually improve its performance. And then you can evaluate some metrics, for example, the accuracy of classification, and making sure that your model can achieve a certain precision level before you launch the model into the real world. For a lot of times, the problems are either too complex for traditional rule-based approaches, or they have no known algorithm. For example, consider speech recognition, because each of us speak differently. We have different accent, we use different words, we use different sentences or styles or patterns. So it is extremely difficult for any written algorithm to, for example, translate speech to text, or vice versa, or do the translation from one language to another language. So therefore, the best solution, at least to date, is to write an algorithm that can learn by itself, given many examples, recordings for each word or each sentence or each paragraph. So when the model learns from more and more data, the performances get better and better. There are many other machine learning examples that we can talk about. For example, image classification and object detection. So image classification is the task of using computer visions to classify images containing different objects. For example, whether it's a cat or it's a dog in the image. Whereas object detection is another very popular computer vision tasks in which the machine tries to identify one or multiple objects from a single image. For example, here in this image, we have 2 cats, a dog, and a duck, a toy duck. Machine learning algorithms are also used in speech recognition extensively. For a lot of time, we need to transcribe speech into text or vice versa. And a lot of time, we need to classify speech by person or by language. Or sometimes we need to translate speech in one language to another language. In finance, machine learning has been used to, for example, predicting stock prices and fluctuations. And of course, we need to mention that the social media, for example, Twitter and Facebook and movie recommendation system, for example, Netflix, the underlying use recommender system powered by machine learning models to make recommendations of your peers and friends and movies and other products. Machine learning models are also the underlying power for modern chatbot, no matter it is a companion chatbot or therapeutical chatbot that are often used in mental health diagnosis and treatments. And not to say that machine learning models, especially image recognition and segmentation models, are widely used in self-driving autonomous vehicle. There are many other sample applications of machine learning models. For example, machine learning models have been used to analyze images of products on a production line to automatically classify them. Machine learning models have been used to detect tumors in brain scans. Machine learning models have been used to automatically classify news articles or automatically flag offensive comments on discussion forums. And machine learning models have also been used to summarize long documents automatically and used to create, for example, chatbot or personal assistant. And machine learning models have been used to forecast a company's revenue next year based on many performance matrices and are used to make your app react to voice command. And machine learning models are widely used to detect credit card fraud. Machine learning models are also used to segment clients based on their purchases, so you can design a different marketing strategy for each segment. And also used to represent sometimes complex, high-dimensional data set in a clear and insightful diagram. And not to say they are used extensively to recommend a product that a client may be interested in based on past purchases, and also being used to build an intelligent bot for a gaming product. Those are probably only scratching the surface of many profound applications that machine learning enables. If we talk about the types of machine learning systems, there are 4 major types we can talk about, including supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So first, let's talk about supervised learning. In the supervised learning setting, we need to provide both the training data as well as the labels to the learning algorithm. For example, we can provide a number of emails, and we also label each email, whether this email is a spam or a regular email, to train a spam email filter. In the regression problem, we can feed our data, including different features, as well as our target value, which is continually distributed to a model, so that the model can learn from the data. And after that, after the model is trained, we can provide the values for the new features so that the model can predict the output, which is a continuous target for us. For example, if we want to use the number of bedrooms to predict the housing value, and then the housing value is a continuous variable measured in US dollars, and then the features are the different number of bedrooms of a house. So when the model is trained, when we provide a house with 4 bedrooms, the model is going to predict the dollar value of that house for us. There are many commonly used supervised learning algorithms. So here are some popular ones, including k-nearest neighbors, linear regression, logistic regression, support vector machines or SVMs, as well as decision trees and random forests. Another important type of machine learning is unsupervised learning. Instead of providing both the data as well as labels to the machine model as in supervised learning, for unsupervised learning, we only need to provide the unlabeled training set. These are some of the commonly used unsupervised learning algorithms. We can classify them into different types. The first type is called clustering, including k-means hierarchical cluster analysis, or HCA. The second type is anomaly detection and novelty detection, basically detecting the outliers from a distribution. Some of the commonly used models include one-class SVM and isolation forest. The third type is visualization and dimensionality reduction. Commonly used models include principal component analysis, or PCA, and kernel PCA. So here we see an example of clustering, which is one type of unsupervised learning. So because we do not provide the labels to the data, so therefore the output of the data are clustered of those original data, but with no label attached. And unsupervised learning is very useful, for example, in client segmentation, in which we try to classify clients with different features or characteristics into different categories, so that targeted advertisement or promotion programs can be used to customize or target those different client subgroups. Another example of unsupervised learning here is that we use the TSNE visualization, is one specific unsupervised learning algorithms to highlight the semantic cluster. So here we provided a large number of images of different objects, for example, automobile, truck, ship, airplane, deer, horse, cat, dog, bird, and frog to the algorithm, but without telling the algorithm what the images contain, or basically we do not provide a label to the algorithm. And then the output is a 2-dimensional visualization, basically showcasing the distributions of those image representations in a 2-dimensional space. As we can see that the TSNE visualization did a pretty decent job of clustering and separating different images of different types. For example, the deer and horse tend to be a lot closer, and cat and dog seem to be close, whereas the bird and horse are separated with a long distance. And also the airplane, automobile, ship, and truck, they tend to be far away from those animals. So therefore, although the TSNE visualization is agnostic to the image labels, actually it detects some similarities and differences between those labels. So the semi-supervised learning is a mix between the supervised and unsupervised learning. It is an approach to machine learning that combines a small amount of labeled data with a large amount of unlabeled data during the training. In the graph below, as we can see, there are only 7 labeled observations, including 3 triangles and 4 squares, whereas the green dots are not labeled. And based on the machine learning algorithm, we are trying to assign the unlabeled dots into one of the 2 categories represented by the triangle and squares. The 4th type of machine learning is called reinforcement learning, in which an agent is trained to choose some options based on certain incentives. So here in this textbook example, the agent tried to make a decision whether to approach the fire directly or to grab some water and then pull out the fire. So if the agent moved directly to the fire without holding some water, the agent is going to get some penalty, or basically points reducted from the overall points. Whereas if the agent try to grab some water and then move close to the fire, try to pull out the fire, and then the agent is going to get some positive points or rewarding. So the agent goal is to maximize the overall number of rewards or points. So therefore, over time, after many experiments, the agent is going to get smarter and figure out that he or she has to grab some water first before moving to a fire. Reinforcement learning has been widely used in the gaming environment, in which people try to optimize and simulate the behavior of the agents in a complex gaming environment. And now let's talk about the main challenges of machine learning. There are at least 6 major challenges that we want to talk about, including insufficient quantity of training data, non-representative training data, poor quality data, irrelevant features, overfitting, and also underfitting. First, machine learning often suffers from insufficient quantity of training data because many of the state-of-the-art machine learning models are trained on huge data sets, millions of images, and gigabytes of text data. So in 2001, some Microsoft researchers published a very influential paper called The Unreasonable Effectiveness of Data, in which the researchers showed that very unintuitively, different machine learning algorithms, including some of the fairly simple ones, performed almost identically well on a complex problem of natural language processing once they were given enough data, as shown in this image. Now, if we provide a small number of data, then we do see a large discrepancy between the 4 different algorithms denoted as memory-based, Willow, perceptron, and naive Bayes. But as we provide more and more data, all the 4 model performances tend to improve significantly. And also, except for the memory-based, which is the most naive and simple type of model, all the other 3 models performed relatively equally well when we were given millions of words as the input. So therefore, with little data, there's a huge discrepancy between the model, and even the most sophisticated model may not perform very well. But if we give enough data, and then even simpler model can achieve state-of-the-art performances. This really showcases that the quantitative data is very important when training machine learning models. And in many times, we don't have representative training data. For example, if we study the relationship between GDP per capita and life satisfaction in a country, we only have certain countries, but we do not have the countries denoted in the red square. For example, Brazil, Mexico, Chile, Czech Republic, Norway, Switzerland, and Luxembourg. If we do not have those data, we only have a number of countries denoted by the blue dots. And then we can estimate a linear regression between GDP per capita and life satisfaction, denoted by the dotted blue line. But when we have gathered more and more data, we get those countries represented by the red square into the model. And then we found actually the previous model without those data points significantly overestimate the relationship between GDP per capita and life satisfaction. When we add back those data points, we see the relationship between the two are significantly attenuated. So this showcases that if we do not have representative training data, most likely our model estimation is biased. And many times, our model also suffer from poor quality data. If, for example, some instances are clearly outliers, then maybe it could be helpful for us to simply discard those outliers or try to fix the errors manually if those outliers denote some data entry or measurement errors. But the situation can become more complicated if, for example, some instances are missing a few features. Say 5 to 10% of your customers did not specify their age or gender. Then you must make some decisions, and of course those decisions are going to have a consequence and have some kind of trade-off that you need to weigh in. For example, do you want to ignore those attributes altogether? Or do you want to get rid of those instances with missing values? Or do you want to fill in the missing values? For example, filling the missing values with the median or average age. Or you want to train one model with the features and one model without the feature with missing values so they can cross-compare and do some sensitivity analysis. So the bottom line is that when you have poor quality data or missing data, you have to do some additional exploring and decision making. In many cases, there are irrelevant features in our data set that we need to make a decision upon. A critical part of the success of machine learning project is coming up with a good set of features to train on. And this process, we call it feature engineering, involves the following steps. First, we need to select the features. Most likely, we try to select some useful features to train on among existing features. And also, we are likely to do some feature extraction, basically combining the existing features to produce a more useful feature. And we may also create new features by gathering some new data. So there are a lot of decisions to make and a lot of efforts to spend when we do the feature selection, feature extraction, and new feature generation. A very common problem in machine learning is overfitting, when the model is possibly too complicated for the small sample data set, and the estimation become very volatile and not trustworthy. For example, here we only have 100 observations about GDP per capita and country-level life satisfaction, and we estimate a complicated model. And as you can see, the model estimations really jump around and fluctuate violently. It may not be trustworthy to believe that when the GDP per capita changes a little bit, the country-level life satisfaction is going to move from positive to suddenly zero or even negative. So the overfitting happens when the model is too complex relative to the amount and noisiness of the training data. And there are different solutions. First, you can simplify the model by selecting one with fewer parameters. For example, choosing a linear model instead of using a high-degree polynomial model, by reducing the number of attributes in the training data or by constraining the model. And second, you probably want to get more training data if it is an available option. And you may also want to reduce the noise, basically by fixing the data errors and moving outliers in the training data. So regularization is a common approach to constrain a model so that the model becomes simpler and then reduce the risk of overfitting. The amount of regularization to apply during learning can be controlled by a hyperparameter. And of course, the specific hyperparameter differ for different models. So a hyperparameter is a parameter of learning algorithm, not of the model. So therefore, it is not affected by the learning algorithm itself. And you must set the hyperparameter prior to training, and it remains constant during the entire training process. So if you set the regularization hyperparameter to a very large value, and then you will get an almost flat model because the regularization essentially reduces the outliers of the trainable weights, so that the slope usually are attenuated when you perform regularization. And if the regularization is too much, and then the model is not really predicting that much because the slope are essentially approaching zero. Let's take a look at example of regularization. First, we train the data on GDP per capita and life satisfaction using the entire data set. we train a linear model denoted by the dash red line. And then consider that we do not have the country level data represented by the red square. And we are only left with the blue dots data. And if we train a model only on those data, we'll fit a linear regression denoted by the dotted blue line. As you can see, if you compare the dotted blue line with the dashed red line, the dotted blue line greatly overestimate the relationship between GDP per capita and life satisfaction. The slope is a lot steeper. And when we apply regularization to our data, we fit the linear regression represented by the blue line in the middle. As we can see, this line is a lot closer to the red line using all the data and have a much flatter slope in comparison to the unregularized linear regression fits represented by the blue dot line. So therefore, the regularization tend to reduce overfitting so that we have less biased result. On the contrary, in a lot of time, we are also underfitting the training data. So the underfitting is the opposite of overfitting, and it occurs when the model is too simple instead of too complicated to learn the underlying structure of the data. For example, a linear model of life satisfaction is prone to underfit because the reality is just more complex than the model. So its predictions between the GDP per capita and life satisfaction are bounded to be inaccurate, even on the training examples. In comparison to the overfitting, the underfitting is possibly has easier solutions. So first, we can select more powerful models with more parameters. We can also feed better features to the learning algorithm using feature engineering approach. We can also reduce the constraints or regularizations on the model. And now let's talk about testing and validating machine learning models. The only way to know how well a model will generalize to new cases is to actually try the model on the new cases, because that is the only way and the golden standard to test the performance of a model. And to do that, you need to split your data into two sets, the training set and the test set. You train your model using the training set, and then you test the model using the test set. And the error rate on the new cases is called the generalization error. Basically, they are out of the sample error because they are not used to train your model. And by evaluating your model on the test set, you can get an estimate of the generalization error. And this error tells you how well your model will perform on instances it has never seen before. It is common to use 80% of the data for training and hold out 20% for testing. However, of course, the exact split depends on the size of the data set as well. If your data set contains, say, 10 million observations, then holding out even 1% means that your test set will contain 100,000 observations. That is probably more than enough to get a good estimation of the generalization error. Now let's briefly talk about the commonly used modules or libraries pertaining to machine learning in Python. The scikit-learn is the backbone for doing machine learning and probably the default and the most widely used library for doing machine learning models. And NumPy is a fundamental package for scientific computing, especially array manipulation and operations in Python. Pandas is a very popular data manipulation and analysis tools in Python. And Matplotlib is the most widely used visualization tools in Python. We are going to use scikit-learn extensively when we move into the machine learning modules, and we will also frequently use NumPy, Pandas, and Matplotlib for data manipulation, management, and visualization. Jupyter Notebook is an open source application that allow anyone to create and share documents that contains code that can be executed right away, as well as arbitrary number of equations, visualizations, and narratives. And Google Colab hosts a version of Jupyter Notebook that allow you to embed text and live code into a single IPYNB document that can be used in Google Cloud Computing as well as sharing with your collaborators. In the subsequent modules, when we learn machine and deep learning, we are going to use Google Colab extensively and exclusively. And the great news for Google Colab is that it offers free GPU, which is essential to any deep learning algorithms, because the deep learning algorithms use a lot of parallel computation, and the CPU is way too slow to run those computations. So therefore, we are going to use Google Colab for all later lab sessions for machine learning and deep learning. If you want to learn more about Google Colab, you are more than welcome to take a look of the YouTube short video here. And I'll also make sure to put both the textbook as well as the YouTube short video into our show notes. Thank you for your attention. I'll see you next time.